Uh, all right, we are very glad to have Seshadhri Commander here from UC Santa Cruz. So Seshadhri's research has won numerous best paper awards. I'd not list them all up after the talk, just like we did yesterday for Pravesh. But I'll mention that he got IBM Test of Time Award a few years ago. And today he will be telling us about the long path to square root demonotonicity testers. So with that out of the way, please take it away, Seshadhri.
Thank you. Am I audible? Is everything clear?
Yes, we can hear you.
Okay, perfect. Firstly, thanks to the organizers, Akash, Anand, and Piyush, for inviting me. I'm really happy to give this talk. Unfortunately, due to some unforeseen circumstances, I could not make it in person. So it's going to be this disembodied voice and video of me giving the talk. But in any case, this is the post-lunch session. You're all probably kind of sleepy after a nice Indian lunch. I'm also kind of sleepy being 12 hours away. So we'll manage through. Needless to say, please stop me at any point, ask questions. This is a tutorial and is meant to, is meant to make sense. And, I don't mean to go too fast. I don't have to finish my slides, so on and so forth. So, with that, I'll begin. This talk is on the long path to square root D monotonicity testers. There's a pun over there that, I think you'll see at some point. Before I begin, I like to credit people who have who really influenced my path. My undergraduate advisor, Manindra Agarwal, my PhD advisor, Bernard Chazelle, my longtime mentor, Mike Sachs, and Tammy Kolda and Ali Pinar at Sandia National Labs, who really helped me frame my research career. This work is with two, again, longtime collaborators. First is Hadley Black, who was my master's student and who is now going to Baruch College as a faculty member. And my long time collaborator, Deeparnab Chakrabarti, who's at Dartmouth. There's an interesting TIFR story here that Deeparnab and I actually met for the first time as summer students at VSRP in TIFR. This is TIFR Bombay in 2002. And that's when we bumped into each other and started talking. I don't know, we became friends. We also started talking some math. And since then, we've always been working on something together. And this work, a lot of it is a collaboration that started with him more than a decade ago. So the point of this, this first part, which is the first 1.5 hours, is to be a fairly leisurely description, of the main ideas in this problem. And you'll see it's a long history of work on this problem. And what I'll try to do is to give you the intuition. And in the second part of the talk, which is, after the break, we'll actually go over some specific details. So the setting that we're studying is, hypergrid functions. So we're looking at functions from a domain to a range. And the domain here is basically just, the d-dimensional grid. So that's n to the d. So n will refer to, the width of the precision of the grid, and d refers to the dimension. And, the special case of n is equal to 2 is just the Boolean hypercube, which we know and love. And of course, this is a very general setting because it involves the line where d is equal to 1. It involves, I don't know, this is like an English test. Has anyone heard the word tesseract? Does anyone know what it actually means?
Was in the Avengers movies.
Yeah, so interestingly, the tesseract is a 4-dimensional hypercube. I didn't know that. So I've drawn that over here. This is the 4-dimensional hypercube, actually has a word. So we're looking at functions on the d-dimensional grid, and the range we look at is actually Boolean, although some of the things I'll say work for general range. And so, because ML is everywhere, sometimes it's useful to think of the dimensions as features. And the function is basically like the indicator of some set, or technically some subset of the domain. And so what you see over here in green that I've marked over here is like some subset of the domain, which can be given by a Boolean function. Often what I will do with my hypercubes or even my hypergrids is to kind of draw them as this tilted cube with the all zeros point at the bottom and the all n-1 point, the largest point at the top. And a function will just be some subset. So this is the basic setting of Boolean function analysis, which many of us know and love. Now, specifically, what happens when you have such an object? So you have such an object which is really an exponentially large object, right? It's exponentially large in D, in the dimension. And if you have a function that is useful or something that comes from an application or something that actually we want to study, it satisfies some property, which I'll call script P. So for now, we can keep it just abstract. It's just some property of the function. And often the question we have is like, if you just get a few values of this function, can you determine if f has the property? And probably not, right? There's no way, because it's an exponentially large object. But often the entire field of learning theory is, can we construct a model function that I'll call g that has the property and is close to this original function f? And what close is, we'll have to define. So the picture, the mnemonic picture that I like to give is like, you have this rectangle here, which is the universe of all functions. You have this set P, which is the property, which is the set of functions of interest. And given a function f, which I've put as this diamond over here, often what you'd like to learn by querying a few points, querying a few values, is can you find a function g which is in the property, which is close enough? So if you look at what a lot of, I'd say, like machine learning does under the hood at some level, is really this task, where maybe this function is being learned through some mechanism. You're collecting samples from somewhere, or you're querying for values. You're trying to learn some model function which has this property. So this framework really covers a large area of of theory and algorithms. And of course, what you'll often have is suppose f is really, really far from the property, whatever, defined appropriately, it might not be worth running an expensive learner. So the learning task can often be expensive, meaning you need to query lots of points to be able to learn a function. And one thing that we'll often ask is, can we quickly determine if our hypothesis, like our belief that f is close to this function, is that even a sensible thing? Is that even something worth doing? And this is where the framework of property testing really enters the picture. So what property testing will say is, we'll say, okay, look at this rectangle here, which is the universe of all functions. Look at your property here, which is in red. We're going to define this region around in yellow, which I'll call the functions that are close to f, epsilon close to f. And what we really want to determine by looking at a few function values is whether f is in the property or f is epsilon far from the property. And the initial motivation given for this, even though it eventually became an entire field of itself, and there are many, many motivations one can give, I think this one is particularly pertinent for this talk that I have, is when learning is expensive, is there a quick way of checking if your hypothesis is potentially true? And so again, like property testing says, does the function have the property, or is it far from the property? And we'll talk about monotonicity, which is a very simple property. This only makes sense when learning is difficult, because if learning is easy, then you'll just try to learn the closest model. Now note that you need some notion of a metric or distance between functions to even formalize any of this. This is where this notion of epsilon far even comes up. And then there is the importance of this proximity parameter, epsilon as we call it, which appears in this framework. So this is just a very high level primer for property testing. But this is something that we often forget, that it actually came initially from this learning perspective, which I think makes a lot of sense for monotonicity. So, with that high level framework out there, what we're specifically looking for, again, we're studying a property called monotone hypergrade functions. So what is a monotone function? A function is monotone if for x less than y, f of x is less than f of y. Now, what does x less than y mean? This is the natural coordinate y is partial order. So x is less than y if all coordinates of x are less than all coordinates of y, right? And there's a less than equal to there, but you know what I mean. So essentially, x is less than equal to y if all the coordinates of y are less than equal to all the coordinates of x are less than all the coordinates of y. And so one way that I've drawn this over here is really you take your domain and you put arrows, you put directed arrows, you make this a DAG, and essentially it's reachability in the DAG that determines if one point is less than another. And a function is monotone if when x is less than y, f of x is less than equal to f of y. Very simple. The most simplest example is a sorted array. And in the case where it's Boolean, like I've drawn a little picture over here of what a monotone set would be, right? So it's sort of upward closed. And monotone functions appear in many, many applications. And again, like initially, a lot of this did come from learning theory, where a lot of concepts that people were trying to learn would be monotone. And even now, like a lot of concepts that are actually learned would be monotone. So for example, if you do spam detection, like is this email spam or not, your features will often be, various things about the email that are indicators of whether it's spam. And usually these are monotone features, meaning that if you have more misspelled words, you're more likely to be spam, so on and so forth. Okay, so this is what a monotone function is. At this point, if there's any question, this is a good time to ask because we'll be talking about monotone functions for the next, I guess, few hours. So your evening is going to be full of monotone functions. Hopefully it's not boring, but it is monotone. So any questions?
Questions?
Okay.
There is a question.
Yeah.
In the slide, there's a comment that equally think of f.
I'm sorry, I didn't get that.
Hello? Hello?
Yeah.
Okay,
Yeah.
good.
Yes.
So there is a comment in the slide that think of f as an indicator of for a set, but how is that equivalent? That's just true of any Boolean function, right?
Just for Boolean. Yeah, for Boolean functions, because
So
for Boolean, yeah, just Boolean.
It's confusing because if the last point is like f is monotone.
So monotone, okay, so f of x, basically if it's 0 or 1, then what it says is if f of x is equal to 1, then for all y greater than x, f of y is also going to be 1. So just think of it as a monotone set, like this picture over here. So if you have a point in here which is in your set, and the function is monotone, or the set is monotone, then every point that dominates this is also in the set, according to this partial order. Does that answer your question?
Yes, it answers this question.
Okay, good. So again, we're talking about Boolean functions here. So Boolean functions are basically subsets of the domain. Okay, so I will proceed. So the property of interest is property of being monotone. And before, to do any property testing or anything, we need to have a notion of distance between functions. So given any function, I can say, what is the distance to monotonicity? So that was the minimum number of changes you need to make to this function or to this set to make it monotone. And we divide by the size of the domain, right? And so this gives us what we call epsilon f, which is the distance to monotonicity of f. This is a quantity between 0 and 1, amen. This is where all the definitions, this is where everything starts. So I've drawn a little cartoon over here. So maybe the best way, the quickest way, the easiest way in terms of the number or the minimum number of changes you need to make to this function to make it monotone would be, maybe you have to add this blue portion here and you have to delete this, I guess, cream portion here. And so the total number of points in the add plus the total number of points in the delete, that is the minimum number of changes you need to make, and we'll divide by the size of the domain to get things between 0 and 1. Formally speaking, this is the Hamming distance, normalized Hamming distance between functions. And so we're just saying the distance to monotonicity is, formally speaking, we're looking at the L0, our Hamming distance between functions represented as vectors. And we're looking at the minimum over all possible monotone functions, again, divided by n to the d. So this is epsilon f, which is the distance to monotonicity. This is saying how far is my function from monotone? How much do I need to change to make it monotone? And again, like we're just talking about sets over here. So it's just about addition and deletion to, to change the function or to change the set. Any questions? This is an important definition. So if you haven't seen this before, please do ask me questions if there are any doubts.
Again, any questions?
Okay. All right. I think I'll proceed. So what is the problem of where does monotonicity testing come up? So there's a very classic result of Bhruti and Tamon, and recently some work by, relatively recently by Lange and Basilian, which is if you want to learn a monotone function, how much of the function do you need to see? And it turns out you need exponential in square root d, which is the dimension, exponential in square root d queries to learn the monotone function, and it is possible to learn with that many queries. I'm skipping over like some extra log factors in the exponent, but what this basically says is a monotone function is a very complex object, and you need exponential in square root d. So this is non-trivial, but it is still exponential. Exponential in square root d queries to see this. Queries is like, how many function values do you need to see? And the property testing problem, remember, as we said, is now you're given the set of monotone functions. Your function is here. You're trying to distinguish, is it monotone or is it far from monotone? Is it really worth running my learner? Just this simple question. And so the setup is, given a parameter epsilon, distinguish between a function that is monotone, which means its distance to monotonicity is 0, versus being far from monotone, meaning that its distance to monotonicity is strictly greater than epsilon, and do this with high probability. So with like probability 2/3, and again, this is something that can be boosted. So just think of it as a classic randomized algorithm. And so our aim is to distinguish between these settings. And the question that was asked by in the initial papers was, can this be done in polynomial in D queries? Because learning is going to take exponential in D, square root D. Can one actually do this in polynomial of D queries? This task of distinguishing whether a function is monotone or far from monotone. Can this be done much faster than it takes to learn? So this was the original question that was asked. And so let me give you a little bit of jargon about this, and then if this doesn't make sense, don't worry. The jargon isn't important, but I think it's for those who are familiar, this is useful. There's a notion of a one-sided tester. So really, one-sided tester just means that the tester always has to accept a monotone function. So specifically, you want, given a function that is far from monotone, you have to discover a violation with high probability. So a violation basically means what we want is a randomized procedure, given a function that is far from monotone, has to discover 2 points x and y, so that x is less than y, but f of x is equal to 1 and f of y is equal to 0. So x is in the set, y is not in the set. So 1 is inside and there's a point above that's outside. This is a certificate that the function is not monotone. And so our aim is to really design a tester that, given a function that is far from monotone, quickly discovers such a certificate. Now, obviously, the function was very close to being monotone. You could not beat exponential time because you'd have to search the entire domain. But if it's far from monotone, one expects maybe this is possible. Moreover, again, this is a technical term here, which I can clarify more if there are questions. The initial search was for what's called non-adaptive algorithms. So all the queries to this function, that all the points that you're looking at are made in advance. The tester gets all the values and then has to decide, is this function monotone or not? Or it has to find this violation. So it makes all the queries in advance in one go. And this is a very deep question as to whether that is required, which I'll come back at the end of the talk. But this is the setup over here. This is called the non-adaptive one-sided tester. But again, the one-sided just means that if your function is far from monotone, you do a bunch of queries, you have to find a violation to monotonicity, which is like a point in the set, and then you go above and a point that is outside the set. Okay. I'll pause here if there are any questions. All right. And so this question was first posed more than 25, I guess about 25 years ago, by Goldreich, Kohlwasser, Lehman, Ron, and Samorodnitsky, by Raskolnikova in her master's thesis, and also a paper by Doris, Goldreich, Lehman, Ron, Raskolnikova, and Samorodnitsky, 99, that they asked, what is the non-adaptive complexity of monotonicity testing for the hypergrid domain and Boolean range, which means how many queries do you need to perform this task? That's the question in this non-adaptive setting. So non-adaptive means you have to make all the queries in advance. And how many queries does it take to find a violation in a function that is far from monotone? This is the question. And this question just by itself has led to like 2 decades of history, more than 20 papers just on specific cases of this problem. And it's been a very rich and fruitful journey. And what I'd like to tell you is about the theory that emerged from the study of this seemingly very simple and crisp problem. So this is the problem definition. And just to give you a starting point of what the very first result on this was, and this was in both these results, GGLRS and DGGLRS 2000. So what they said is like, you can look at this, and let's just look at the hypercube, which is even a simpler setting. The hypercube is just, where n is equal to 2. Suppose you sampled a uniform random edge of the hypercube. So then edge of this hypercube, and you query both points, f of x and f of y. And you just, you try to see, is this a violation? So if this is a violation, then your function is not monotone. So what does a violation mean? You find a lower endpoint in the set and the upper endpoint outside the set. Just this simple test. And what they proved, which, in the second part of the talk, I'll show you the proof of this, a very nice, elegant proof, that the probability of finding a violation is at least epsilon f divided by d. So actually what this says is that if epsilon f is large, think of it as being a constant, then essentially d samples, d over epsilon samples suffice to detect a violation with high probability. So what this means, if you just sample these edges, you'll find a violation with high probability. A violation is again lower endpoint in the set, upper endpoint outside the set. And this, from here, you're going to see, why is it that I decided to do this talk for this workshop? We're talking about algorithms, and we'll see where basically geometry is going to enter the picture in trying to understand this. And it's going to lead to a geometric theory of understanding this problem. Okay, so this is called the edge tester, which is basically finding an edge of the hypercube. And if you think about it, it's got something to do with the boundary of the set, like some sort of up boundary. You're trying to find something is inside the set and outside the set, but except in this directed notion. Directed because you want y to be greater than x in the partial order. And what DGGLRS showed was that also there is a d log square d over epsilon monotonicity tester for hypergrids. Now this, for hypergrids, you don't choose a random edge. You actually have to choose something called a random line. Things are more complicated over there. But to some extent, you also get this O of D tester. Now, this is sort of extremely interesting that this is even doable, because to learn the monotone function, you need exponential in square root D. But to just test whether the function is monotone, just to quickly check, is this close to monotone or not, all you need is D. So there's a huge difference. And this is where the interest in monotonicity testing arose, that one can do this much faster. So any questions at this point?
Just one moment. So is this the non-adaptive setting, the result?
This is the non-adaptive setting, yes.
That's it.
Yeah, this is the non-adaptive setting. So I hope everybody is following. I mean, Akash, I'll sort of trust you to be my eyes over there and make sure that people seem to be following, not dozing off. Okay. So the question, of course, is, is this D bound optimal? Again, think of epsilon as a constant. So don't worry about the dependence on epsilon for now. So now, again, the previous result that I gave is for Boolean functions, although it's an equally reasonable tester even when the function is real valued. So it also works for the real values, or actually it's a reasonable tester. Whether it works or not is a more difficult question. But this result over here is only for the Boolean setting. It's only for the Boolean setting. What Blaise, Brody, and Matloff showed in 2012 was that actually, if the range is real, then there is a lower bound of omega d. So this would be, you cannot beat d when the range is real. And a couple years after that, or within a year after that, Deeparnath Chakrabarti and myself proved that actually when the range is real, when the range is arbitrary, d is the correct answer. Moreover, for hypergrids, the answer is d log n. So we nailed down the complexity, and there's a theta there, and the theta even has an epsilon in it. So it sort of, it completely resolves the monotonicity testing problem for hypergrids when the range is real. So for arbitrary ranges. And it turns out that actually this edge tester is the one that gives the D bound. The log n is more complicated, but the D bound. And sort of what you get here from an algorithmic perspective is the best possible setting. The upper bound is actually a non-adaptive one-sided upper bound. So the upper bound is a non-adaptive tester, but the lower bound is adaptive two-sided. So it says that even if you do adaptive algorithms, even if you do two-sided, you can't beat this bound. And at this point, it's like, okay, finish, end of story. We can go home now. The optimal tester for the hypercube is the edge tester. We're done. So around 2013, around this time, this is what we thought. And the question is, does a Boolean range make the complexity any lower? It didn't look like it because there were no techniques to show that. There was a result of Fisher, Lehman, Newman, Raskolnikov, and Rubenfeld, 2002, which showed that there is a square root D one-sided lower bound. So this was sort of the knowledge around 2012, 2013. And can we beat D? And indeed, the reason for this talk is, is because we actually can beat D. And
Seshadhri, there is a question.
Yes.
So can you go back to the last slide?
Yes.
So this is a D log square D for a hypergrid?
Yes. Because actually this tester, it's a different tester. It's not really just choosing an edge. It actually chooses a line of the hypergrid and then does something in that line, does some sampling in the line. And because
there is no dependence on N here.
There is no dependence on N here. That's a very good observation. There is no dependence on N here.
The tester that you get, like your 2013 paper,
Yep.
There you show that the lower bound is D log N, or yeah.
Okay, good question. Good question. Thanks for pointing that out. So clearly you're awake. Good. So this lower bound here is when the range is real. This D log square D is when the range is Boolean.
So in the case of Boolean, it doesn't matter if you're in, so N wouldn't really matter here.
N doesn't enter, but an interesting question is, do you really need the log square? There's seemingly a small gap. Do you need the gap? But the gap is very small.
Yeah, thanks.
Yeah.
There is another question.
Yeah.
So you've mostly talked about the sample complexity. So what about the running times of these algorithms? Are they polynomial?
Yeah, so the running time is linear in the number of samples. Yeah, and I should be a little precise that it's not samples, but queries, because, you can query any arbitrary point. And like the edge tester, it queries one random point and then a random neighbor. But yeah, you're right. The query complexity and the running time are essentially identical. Any other questions?
I think that's it.
Okay, good. Okay. Yes, excellent observation that there is a dependence on N when the range is arbitrary, but when the range is Boolean, it seems the dependence on N disappears. So And the question is, can we get little o of d complexities? Do we really need this dependence on the linear dependence on the dimension? And it turned out sort of soon after that, Deeparnab and I showed that we get for the hypercubes, not for the hypergrids, for the hypercubes, you get a d to the 7/8 query tester. And it seems like, now you might say, why 7/8? The point was we actually got something better than d, which at that point was a surprise because, given the previous results, it seemed like d, that edge test is the natural answer. Then Chen, Servedio, and Tan very quickly after tightened our analysis and gave a d to the 5/6 query tester. And then in a big breakthrough, Kotminzer and Safra gave a square root d query tester. All these results have the same procedure. It's all just in the analysis that they give this improvement. And at least for non-adaptive algorithms, this is the end of the story. So Chen, De, Servedio, and Tan, but then Chen, Weingarten, and Chia showed a square root d two-sided non-adaptive lower bound. So this kind of, for non-adaptive algorithms, kind of closes the story here up to log and epsilon dependencies. And what emerged from this work was a theory of something called directed isoperimetric theorems, which I will talk about, which is much of what the talk is about. And seemingly these were hypercube specific. And the question at some point was, could they generalize? Can you get results like this for the hypergrid? Because when n is equal to 2, things seem to work. But even when n is equal to 3, many things broke down. And so to give you the history over here, so the initial result, as I said, again, there's an independence on n here, because again, the range is Boolean. The range is Boolean. All of this is Boolean range. Dodis et al. Gave a d log square monotonicity tester. Berman, Raskolnikova, Yaroslavtsev improved it to d log d. And then with Hadley, Black, and Deeparnab, we got it down to d to the 5/6. Then we had a result, and then Braverman, Cote, Kindler, Minzer had a result where people got a poly n square root d. So you got the exponent of d correct, but then there was a polynomial n dependence. And then finally, we got a d to the half plus little o of 1 query tester. All of the testers over here are actually different. It's not one canonical tester. And so this d to the, so what it says is the square root d, this exponent on d is something that is achievable even for hypergrids. And this sort of resolves up to this d to the little o of 1 factors, resolves the question of the non-adaptive complexity of monotonicity testing for hypergrids. So the question was asked in 2000. Finally, in 2024, we had a resolution. And let me also justify why hypergrids are interesting. I mean, other than the fact, well, they're sort of obviously interesting as a generalization of the hypercube. But the nice thing is that if you take the hypergrid, then, okay, so for example, let's just take the hypercube where instead of a uniform distribution, you actually had a product distribution which was biased. So each point with probability p and 1 minus p. So a biased distribution on the cube. So you can also define property testing on the biased distribution where distances are defined with respect to that. And then it's not clear that the hypercube results will generalize or work. But the nice thing is that you can always transform such a setting to a uniform distribution on the hypergrid. So to cut to the chase, basically when you get results for the hypergrid, it works for any product distribution automatically. There's just like one simple transformation that does it, which is really nice. So then the uniform distribution on the, like the product distributions on the hypercube aren't a special case. Everything just works out. You can even set n to be infinity. So you can even let the domain be r to the d, and then you can define monotonicity testing for measurable functions over product distributions, and everything sort of checks out very nicely. So hypergrids are very nice because then it immediately gives you results for product distributions. This is somewhat of a technicality. But before I go on to my bad question, my bad pun, any questions at this point? All right. So I'll ask you a bad question, and you probably won't laugh, but still. The question is, why did the baby grid not get any sugar? And the answer is because it would become a hypergrid. I don't know. I guess any parent in the audience would understand that. You don't give babies sugar because they get hyper. But anyway, that's Terrible joke. Now let me tell you about the interesting mathematical aspects at the core of all of this. It's a phenomenon called directed isoperimetry. And it's all about
There is a
surfaces.
question, Seshadhri.
Yeah.
So you said that when you put n to infinity or something along those
Yeah.
lines, you get how would that be how would the domain be R to D? I mean, is there some technical detail or?
So think of it as okay. So you have to be a little careful. So technically, one has to define a probability measure,
Right.
and you can define any product measure, but the domain essentially is R. So you could basically say in each dimension, the measure is the Gauss. So you could take the Gaussian measure, for example.
But the set itself would be discrete, right? Like n
No,
to
so the
power
set
d.
will end up being continuous. So think of it as your set is going to be some continuous set.
Okay, thank you.
Right, just think of it as the grid. As the grid becomes finer and finer, it just starts looking like the plane, or just like space. Yeah.
One more question.
Yeah.
Hey, could you pick a partial order on n? Would these questions be interesting even if?
So, that's an excellent question. Like, what if you had some sort of different partial order? Like, so currently, I'm
Partial
taking
order
the
to the
total
d, I
order.
guess. Yeah. Pick a
If you have,
partial order.
I'm sorry.
You pick a partial order on some discrete set and raise it to the d.
That's a great question. So it is not at all obvious that you would get square root d in those settings, but I believe it is doable. But that's an excellent question. And indeed, a lot of the techniques that we recently developed seem to generalize to that setting. But it is by no means obvious. It is by no means obvious that you can get a square root. Halevi and Kushelevich studied this problem to some extent, and they have, I think, the only results on this. And I think you get in the product, you'll get some. I mean, you can get some non-trivial results, but yeah.
Also, in this product distribution, is it that the distribution has to be tight in some? So it's like its mass does not like this is mass towards infinity is 0. Is that?
You mean in the real case?
Yeah. Like.
I mean, I guess naturally, just if you have any product on just any measure on R, I mean, at some point you're going to have, as it tends to infinity, the probability mass has to go to 0, right? Because like the probability mass of things beyond a point have to go to 0 as that goes to infinity.
Okay. Working with some tightness kind of thing that like you for every epsilon you'll find some bounded set that the mass in the bounded set is at least 1 minus epsilon.
No, I don't. You don't need any condition of that form. All you need is as long as you define. Okay, so as you correctly sort of surmise, like, you have to be a little careful with the definitions, but as long you can take any notion of a measurable function over a product distribution and things will check out. Because in some sense, if you look at what does it mean to be measurable, it really means that you can break it up into grids of sufficiently fine granularity and take a Boolean function there and like take the limit of that. So then once you get this independence of n in the testers, then you just get it for R. Any other questions?
That's it.
Okay. All right. So let us move on to this phenomenon called directed isoperimetry. And I think this is of interest even if you didn't care about any of these questions. There's just something fundamental about the Boolean hypercube. So let's go back to this edge tester, which we discussed. So you're sampling an edge uniformly at random. You're querying both the endpoints and you reject if it's a violation. You're just checking, like, does this, sort of cross that boundary? And we said the probability of finding a violation is at least epsilon f over t. Now I'm going to sort of give you another perspective to this result, a geometric interpretation. So let me again look at, I've just sort of blown up the picture. So this is my hypercube over here, and this is my set. Now, what are the violated edges? These are exactly the edges that start from the set and point upwards. And let's just assume that this set is a far from monotone. So I've drawn as an arrow over here, like the partial order is going upwards. Of course, it's hard to do d dimensions in 2 dimensions, but this is the best we can do. So what it says is the number of violated hypercube edges is omega of epsilon f times 2 to the d. Like the total number of edges is epsilon f times 2 to the d. So where did that factor d go? The total number of edges is d times 2 to the d. So you'll see that this theorem is equivalent to that. And so this motivates a notion of influence, which I'll call the directed influence, which says the number of edges going from the set to the outside of the set, but I put an arrow to say that this is upwards because this is the directed. So I don't count the edges that are going sort of below. And so the influence is the total number of violated edges, the edges that are leaving the set, divided by 2 to the d. And what this theorem says is that the number of such edges for any set is the distance to monotonicity times 2 to the d, or rather the influence is just the distance to monotonicity. So what the theorem says is that the directed influence is omega of the distance to monotonicity. Now this is super interesting because if you didn't use the direction, if you didn't have this plus, then what you're getting is just the standard notion of influence of a Boolean function, which is at least the variance of the function. Like this is like a classic result that one studies in Boolean function analysis, is basically about the expansion of the hypercube. So let me give you an undirected view and a directed view. So this is also called the Poincare inequality. So in the undirected view, you could take any subset of the hypercube and you ask, how many influential edges are there? So what is an influential edge? It's an edge that goes from the set to the outside. That's given in the left. And the right side, the directed influence is I'm only looking at edges that respect this partial order. So the classic notion of influence is the number of edges that go from the set to its complement. This is divided by 2 to the d. And the Poincare inequality, the edge expansion, the influence bound, so on and so forth, is a classic statement that says the influence of a function is at least the variance of the function. So what is the variance of the function? Again, the technical definition is the number of ones divided by 2 to the d times the number of zeros. The reason you take the variance is you say that, well, if the function was all ones, then you don't really have any boundary left. So again, just think of this as you have a set which is a constant fraction of the total. So if you have any set which is a constant fraction of the total, then the influence is at least a constant. There are at least 2 to the d edges that are at the boundary of the set. And this is where isoperimetry enters the picture, because the influence is like a surface area and the variance is like, it's some kind of function of, it's isoperimetry says surface area is at least a function of the volume. That you cannot have arbitrarily small surface area when you have some volume, and the variance is like a measure of the volume. It's like the number, it's like the size of the set. So you have size of the surface area as the influence, and the size of the set is the variance. And I bring back this, I guess I didn't ask this question as to why did I put this Greek picture here? And this is related to, this is a picture of Queen Dido of Carthage, who was supposedly the first person to have posed an isoperimetric question. And that's why you have the circle there. But this is called the Poincare inequality. This is the edge influence bound, which maybe many of you are familiar with. So giving you a perspective here is that the Poincare inequality says the influence is omega of the variance. This is the undirected hypercube. The Goldreich GGLRS, the edge tester bound, just that tester bound is effectively saying that the directed influence is at least the distance to monotonicity. So it seems like there is an interesting parallel that when you went from an undirected surface area to directed surface area, that's very easy to see, right? You basically take the edges and you direct them and you can ask how many edges are there. But suddenly the variance gets replaced by the distance to monotonicity, which is seemingly very bizarre. Any questions about this? Okay, I'll proceed. So what you have on the left-hand side, the directed expansion or surface area seems to be at least the directed volume. So the distance to monotonicity, which was defined in this very sort of strange way of how many changes do you need to make, seems to play some role of a volume in these statements, in this statement at least. Okay, what I'm going to now show you is that this bound is tight. As a very simple example, a classic example called the dictator function. So what the dictator function is I want to give you a function that is far from monotone. So all I say is look at this coordinate over here, and if the coordinate is 0, I make the function value 1, and if the coordinate value is 1, I make the function value 0. So this is called an anti-dictator. This is like the exact opposite of a dictator. The distance to monotonicity of this function is half. Like you basically have to change either all the 1s or all the 0s to make this function monotone. So you have to change pretty much everything. The number of violated edges is exactly 2 to the d minus 1, right? It's just all edges that are crossing this one dimension, and it's 2 to the d minus 1. The total number of edges in this function is d times 2 to the d minus 1. And so the edge tester needs d queries to actually find a violation, right? Because if it's doing queries at random, it needs d queries here. And this also says that that directed Poincare inequality is tight. The directed influence of this function is basically means like a half or 1, depending on how you measure it, up to constants. And so, questions? All right. So a natural question, okay, so at this point, I'm going to basically say, we talked about this directed Poincare, and I'll tell you, this is sort of the situation that we had around 2012 or so. It's like, okay, it looks like this is some isoperimetric statement, but how exactly would you beat this D bound in such a situation? Now, it seems that to be able to do better than O of D, one needs to do a longer walk. So if you started in this green portion and you did a long upwards walk, so kept flipping bits up, you might end up at this Y, which is outside. And then this is kind of some suggestion that, maybe we should be analyzing a tester that is doing a longer walk than just taking edges. Because if you took edges, you can't beat this bound anyway. So what is the right length to walk? And I'll tell you that the square root of the dimension naturally pops up here. So what we know about the Boolean hypercube is that most of the mass is basically within square root d of the levels of the hypercube. So most points have a Hamming weight, which is plus minus square root d of d over 2. So d over 2 plus minus square root d. The portions that are outside these, called the caps, have extremely small volume, right? So this is basically the concentration of measure. And so what we could do is we could take that dictator function, we could just outside the caps define it to be all zeros below and all ones above. And this is not going to change the function much, because the caps, even though this picture looks like they have a big volume, because I can't draw the Gaussian measure here, it actually has very little volume here, or not the Gaussian, but essentially the number of the Hamming weight behaves, it's a binomial distribution, proximal by a Gaussian. So if you do a long random walk, you can't walk more than root t, because then you'll end up in this region and you won't detect a violation. So you have to walk while staying in the middle layers, and you have to keep walking upwards. And so square root t is the right bound. And then I'll show a very quick analysis of why that's the case. So you can think of your initial starting point is going to be in the green region with probability half. And at every step, your probability of crossing that dimension is about 1 over d, because there's only one dimension to cross where you'll find violations. And if you take square root d steps, you might, sort of say the best you could hope for is square root d times 1 over d. And so it's 1 over square root d probability of crossing this if you did this long walk. Remember that when you do this walk, you only query the endpoints. You don't query all the points in between. right? So you start at X, you do a long walk and query the other point. And so if you did this process, your odds of succeeding for this specific example is 1 over square root d, which beats 1 over d. Because if you just took an edge, there's just a 1 over d probability of hitting that dimension. But if you take a long walk, you do better. Now you might say, why not walk even longer? But we discussed you can't walk more than root d because you'll end up in those caps where maybe the function is just, zeros and one, is trivially defined. And so another bad pun is that the route to root d is to basically take a longer route or a longer path, and hence the title, which was the long path to getting root d. And so the question then that came up is, how do we analyze this tester here? We need some structural insight for functions that are far from monotone to see how to do this analysis. And it's about how do you escape a set that is far from monotone by doing these upward walks. And that is really where directed isoperimetric theorems come into the picture. So this is a good time for me to pause. I think we're about an hour into the talk, a little bit more. I'll take any questions you have here, and then I'm going to sort of dig deeper into the directed isoperimetric theorems. Are there any questions? Okay, then I'll proceed. So now what I'm going to show you is just a quick history, but drawn out in this table. So the undirected hypercube, there is a statement called the Poincare inequality, which is this influences at least the variance. There was a directed version that was proven by Dodis et al. And by Goldreich et al. This is the classic edge tester bound, and you get a D-query tester out of it. So when the influence is omega d, and this is d, and this is tight for this tester. So Margulis in 74 proved, I'll define this shortly, something called the Margulis theorem, which says that the influence times this thing called gamma f is omega variance squared. Gamma is actually a measure of the surface in a different way. And what we proved was a directed version of this statement, where if you had directed versions of this, then you can replace the variance by the distance to monotonicity. And that actually gave a d to the 5/6 tester. So we initially got d to the 7/8, but actually you can do a tighter analysis. Chende, Servedio, and Tan showed that, and you get 5/6. And so Talleyrand had a more sophisticated theorem. Again, I will define this, but just look at it sort of syntactically. You replace this inf with the inf plus, and you get the expected square root of the influence over here. So the expression I'll explain, and you replace the variance by the distance to monotonicity, and you get a square root d-query tester. So it turned out that by taking, and these statements, each one implies the previous one. So Talleyrand implies Margulis, which implies Poincare, and actually the directed statements imply the undirected statements. So there's a partial order of strength of statements here. The Koch-Minzer-Safra theorem basically implies all of these other theorems pretty much directly. There's like a simple calculation that you do, but this is the strongest theorem of all. And this leads to the square root d tester. So the way that we got the improvements from that simple edge tester bound, which is to analyze the path tester, was by proving directed versions of undirected isoperimetric theorems. This is like a quick history of this. Any questions? Okay. And so all these questions are basically a rather fundamental, insight or a fundamental inquiry into how do you measure the boundary of a set. So let me view, because we're looking at Boolean functions, the boundary is like a bipartite graph. The greens here are the ones and the blues are the zeros. Right? So what you have is whatever graph you have here is basically, the boundary is a bipartite graph where you're looking at the edges that go from the green to the blue, which is the ones to the zeros. Now, of course, we're directed it, so we don't care about this lower portion here. which are edges that are going into the set. We only care about the edges that are leaving the set, the upward edges. This, what I call G plus, the violating edges, the subgraph formed by the violating edges, this is really what we care about here. Now, if you're doing the undirected setting, you basically care about both, but in the directed setting, you only care about one of them. This is the directed boundary. How do you measure the size of the boundary? Well, the most obvious thing you can do is to just look at the total number of edges in the boundary. So let me make that a bit more precise. Let me say inf plus of x is the out degree of x in this directed graph. So for example, for this point over here, the out degree is 2. For this one, the out degree is 3, 3, so on and so forth. So what I could do is I could take the average value of the out degree, which is the expectation over all the ones of this inf of x, will basically just give you the total number of edges in this directed graph. It's just the average, right? So I'm summing over all the out degrees and let me just divide by 2 to the d, divide by the total size of the set. So it's an average. I'm abusing notation somewhat over here, but just think of it as I'm averaging over the whole universe, like all points. So the average value of this inf plus x is the directed influence, is the IF. Okay, this is like the total number of edges, the most obvious way of measuring the surface area. Now let me look at this influence a little bit more carefully. So we looked at the anti-dictator case, where the influence is just O of 1. Let me look at another classy example, which is the anti-majority. So what is the anti-majority? If the Hamming weight is less than n over 2, it's in the set, otherwise it's outside the set. Whether you look at directed or undirected, the influence over here is actually square root d, right? This is basically because the size of that middle level is a 1 over square root d fraction. This is just by, the binomial coefficient. This is by, whatever, I guess the Stirling approximation, or whichever way you have it, is that if you look at one of the middle layers of the hypercube, then the size of that is a 1 over square root d fraction. And for that 1 over square root d fraction, all the vertices actually have d over 2 edges that are leaving the set. So you have this interesting trade-off here, that in the left side, in the anti-dictator, every vertex in the set just has one edge that is leaving the set. Whereas in the anti-majority, every vertex has many edges leaving the set. But you have many fewer vertices at the boundary. So what if we also decided to measure the boundary in terms of the size of the set and not necessarily number of edges that are crossing? Now, the set as in, I'm sorry, the set at the boundary. So specifically, what I can do is I can also count something called the vertex boundary. So the influence is like the edge boundary, but the vertex boundary is again dividing by 2 to the d to normalize. Choose any x, which is on the one side, so that it has at least one influential edge incident to it. Right? That's just the vertex boundary. The total influence was the edge boundary, and this defines the vertex boundary. So this is, again, formally speaking, this is, again, the expectation over x or averaging. You're just looking at the indicator. Is the influence more than 0 or not? Now let's look at these two cases. And this is a very important picture to have. If there is nothing else you take away from this talk, but you just take away this image, I think you would have learned something. The edge boundary for the anti-dictator. And I put this in yellow because every vertex in the set is at the boundary. In the right side, only a few vertices are at the boundary. So the edge boundary is O of 1 here, when measured in terms of influence. The edge boundary is square root d here. But on the left side, every vertex is in the boundary. So the vertex boundary is large, but the edge boundary seems to be small. So the vertex boundary is like O of 1. But in the right side, the anti-majority case, the vertex boundary is O of 1 over root d. It's just that yellow part, which is in the vertex boundary. Okay, so the edge boundary here is small, but the vertex boundary is large. And over here, the edge boundary is large, but the vertex boundary is small, at this point, we don't even have to talk about monotonicity. This is just for any set of the hypercube. And the edge boundary, by Poincare, we know that it has to be at least, it's at least the variance. The variance is a constant, so this is the lowest possible. And something called Harper's isoperimetric theorem says actually that this small thing, this is the lowest possible. So what's interesting is that when you minimize the edge boundary, the vertex boundary becomes large. But when you minimize the vertex boundary, the edge boundary becomes large. Is this always true? That you can never simultaneously make the edge boundary and vertex boundary small? Like, it seems, why should that, like, this is somehow where the magic or the mystery of isoperimetry starts entering the picture. Does this, I mean, I want to sort of pause here and make sure that you understand what I'm trying to say here. Any questions? Okay, so either everyone is following or everyone has fallen asleep, and I don't know which one is which. But
I think people are awake and laughing.
I hope it's the latter, not the former. Okay, good. So I just defined the edge boundary to be this influence, which is just like, you know, the average degree of some vertex in the set. And the vertex boundary is just the, again, normalized, the number of vertices at that boundary. Now, what Margulis proved is that the product of these is always large. So what this says is that you can never simultaneously make both of them really small. And I will show, I'll work this out for the examples. And so again, let's go back to this picture here. What is the vertex boundary here? This is like the average, this is the influence, the expectation over X. So I was like, I'm picking a random point, which is, you know, again, which is in the ones, and I'm looking at the average influence, and this is just 1, which is small. But if you look at the vertex boundary, this is really large because everything is in the vertex boundary. The product of these two things is just 1. Now here, the edge boundary is large, it's O of root t. The vertex boundary is O of 1 over root t, but again, the product of these is 1 because both of these functions, you know, have constant variance or constant distance to monotonicity. So again, think of this epsilon being a constant. It's the product of these things is always 1. Poincare just said that the first term, which is just the vertex, the edge boundary is at least 1. So Poincare just talks about the first part and says that is at least 1. But Margulis says even if you multiply that by the vertex boundary, and the vertex boundary is always less than 1 because it's a fraction of the set, you still get something more than 1. And one can then generalize this to the directed setting. And instead of looking at the entire graph, you only look at this top part here. And you can now directed influence and directed vertex boundary just as before, right? We're just ignoring this lower portion here. And with Deeparnath Chakrabarty and I showed was that the product of these is at least epsilon f squared. So now instead of variance, you now get the distance to monotonicity here. And so any questions about just the statement? Okay, good. So just to make sure that how I'm doing on time. So Akash, I have about, I guess, 40 minutes left for this session.
So close to 24 minutes.
24, sorry. Okay, I'm doing my math wrong. 24 minutes. Okay, good. Yeah, so just let me know when they're about, okay, so I'll just put a timer so that I follow. I got confused with the time. So you said about 20 minutes, right? Okay, good. All right. So this is the directed Margulis theorem. And now let me give you, now you might say, why does this have anything to do with, you know, with any of this testing monotonicity? Let me give you a rough analysis for this, what I call the capped antidictator. So remember that we did this thing where we said, excuse me, we said you pick a random point. Now the probability of crossing at every step was 1 over d, but because you did this walk of length square root d, you kind of get a 1 over root d of the eventual chance of getting a violation to monotonicity. Remember, we only query X and Y, just the endpoints. And what we thought is, now by directed Margulis, suppose the directed influence was O of 1. That means a constant fraction of the vertices must be on the boundary. And this looks like a situation, this is a situation like that. Could we just recreate an analysis of this form, just when the directed influence is O of 1? Because if the directed influence was little omega of 1, then you can, the edge tester already beats the D-bound. So at that point, we were just saying, can we just somehow beat this D-bound? And it seemed like this was some entryway into this. Now let me tell you about the Talleyrand theorem. And this is an incredibly deep and surprising statement just about the structure of the hypercube, or actually is basically about any product distribution. So Talleyrand had a very strange notion of surface area. So now I'll go back a bit. Now these are all fairly natural notions of surface area, right? The first one is the number of edges crossing the boundary. The second one is the number of vertices at the boundary. Kind of makes sense. So what Talleyrand defined as his notion of surface area is that you look at all points. It's an expectation, so you're just averaging over them. You look at the square root of their degree. So the square root of this influence. And this is the Talleyrand objective. And what he proved is that this quantity is omega of the variance. Now there are certain justifications for why this comes about. And it's not even obvious that this is stronger than Margulis. But if you do a one Cauchy-Schwarz, basically, then you show that Margulis is actually a direct consequence by Cauchy-Schwarz. I want to explain this statement a little bit more. And as I said, like Margulis also implies Poincare. So what Koopmans or Safra did was they basically gave a directed version of this statement. So now remember, so in the previous version, we were looking at all the points here. We're looking at all the degrees, both the upward and the downward, and we get the statement. So obviously the Talleyrand objective is larger. But when we do the directed version, we ignore the downward part. We only look at this upward part. And what they proved is that the Talleyrand objective is actually omega of the distance to monotonicity again. So again, this very strange phenomenon comes up, which is you take some very, let's say, arcane isoperimetric statement in the undirected setting. You basically put a plus, you convert the undirected to directed, and you replace the volume by the distance to monotonicity, and the statement holds. Why this is the case is still a mystery. What they proved was an even stronger statement called the robust statement. And I want to sort of tell you what this robustness is, because if you encounter this literature at any point, this ends up being quite confusing. Or I shouldn't say confusing, I should say that it feels unmotivated. And so I want to give you an even deeper understanding of what's going on. What they said is, they write the statement of this form that for any edge coloring, the min over C of this strange influence is actually the Talleyrand objective, that this quantity is actually omega of the distance to monotonicity. So what on earth does this mean? And by the way, so they lost a log factor in this, which Pallavu, Raskolnikov, and Weingarten removed in 2022. This is called robustness. So here's what they're saying. Consider this boundary, which is just a bipartite graph. Now, one way of defining this boundary is I take an expectation on the green side, which is I basically average over all the vertices of the square root of the influence. And I could also do the same thing on the zero side, or the one side of the zero side. I've been defining things on the ones, but you could define on the zeros. Let me just take this very simplistic bipartite graph, where what you have are stars. It's a collection of stars. There are 2 to the d vertices on the blue side and the green side. But what you have is half the vertices here have degree D, and half the vertices have degree 1. But they're arranged in this way where the degree D vertices connect to the degree 1 vertices on the blue side, right? So it's just a collection of stars. The degree of each star is D. Okay. Now, if you compute these quantities, you get omega of 1. Why? Because if you look at the green side, half the vertices have degree 1. And look at the blue side, half the vertices also have degree 1, and square root of 1 is 1. But what Kortmans or Safra said is they'll prove an even stronger bound. They'll say, suppose there was an adversary who assigns each edge to either 0 or 1 to minimize this quantity, which means suppose every edge, okay, so I'm just going to, was assigned to one of the endpoints, and you had to count the degree at that endpoint. So specifically what they said is suppose some of these edges were assigned green and some of these were assigned blue. And when you're counting the green quantity, you only look at the green edges. And if you're counting from the blue area, you only look at the blue edges. It's a bit technical. If I'm losing you, don't worry about this. This is somewhat of a technical discussion. But what they basically say is that even if an adversary were to assign these edges to one of the ends and you only counted it from there, you still get a large surface area. And this is just an example where there exist examples where the original definitions, the Talleyrand objective is large, but actually if you do this bicoloring, it can become much smaller. So again, I will leave questions about robustness for later. But the point of the robustness is they prove this robust version of the Talleyrand theorem. And again, what does it mean? So I'm going to give you the meaning sort of very clearly. And I think that this picture should hopefully make sense. So again, let's just assume that the distance to monotonicity is omega 1. Directed Margulis, which kind of makes sense, says that the directed influence times the directed size of the vertex boundary is omega 1. Directed Poincare says that just this directed influence is omega 1. So what does this mean? It means that there exists some r greater than 1 where the influence is r and the gamma, which is the surface area in terms of the set size, is 1 over r, right? So for whatever that r is because the product of these is omega 1. So there's some r for which this happens. So what this means is if you look at that boundary, the number of vertices in the boundary is 2 to the d divided by r. And this is a typo, I'm sorry. It should be the number of edges is r times 2 to the d. Right? This quantity here says that the number of vertices in the boundary is 2 to the d divided by r. And this part says the number of edges is r times 2 to the d. So what would the nicest possible case of this graph be? It would be nice if it was a regular bipartite graph. So what would a regular bipartite graph be? It would be that the number of vertices is 2 to the d divided by r, and all the degrees would be r squared. Right? Why is it r squared? Because the number of edges is r times 2 to the d. So you divide these two and you get r squared. Okay? The robust Talleyrand theorem of Kortmans or Safra actually implies this is what the boundary looks like. The boundary looks like a regular bipartite graph, or rather contains a regular bipartite graph. Now that is remarkable. So what it's saying is, if you look at this nicest situation of what the boundary could look like based on Margulis, then that is actually what is happening in a product distribution or in the Boolean hypercube, which just completely boggles my mind that that should be true. Like it's saying that when you, and I'll give you a picture here, assuming of course the distance to monotonicity is omega 1, if you look at that boundary, you get some sort of weird bipartite graph at the boundary between the vertices in the set and the vertices outside the set, then essentially there exists some r so that the boundary contains a regular bipartite graph with these parameters, where the number of vertices is 2 to the d divided by r and all the degrees are r squared, like in this portion. And this statement is correct up to d to the little o of 1 factors. So there's some loss here, but d to the little o of 1 loss, so ignore that. And so what this says, what the robust directed Talleyrand, this is where the robustness with the coloring and all of that stuff is needed. It is needed to make this claim. And this is really the essence of what the statement is saying. It's saying that in the Boolean hypercube, when you look at the boundary looks like contains a regular bipartite graph with these parameters where there's some r. But so essentially, when r is smaller, the number of vertices shrinks, but the degrees start increasing much more. And again, I'll work it out for our examples. For the anti-dictator, there are 2 to the d vertices on the boundary, each with degree 1. So the boundary size is 2 to the d. All the degrees are 1. So r is equal to 1 for the anti-dictator. For the majority, there are 2 to the d divided by root t vertices on the boundary, and each has a degree d. So here the r is actually square root t. And so essentially it says for any function, which is far from monotone, constant far from monotone, any function will have this property. That you have a boundary size of 2 to the d divided by r, and you have a regular bipartite, it contains a regular bipartite graph where the degrees are r squared. I mean, this is even and this also holds in the undirected setting. So even if you ignore the directed part and you don't care for monotonicity, this is just a statement about what the boundary of any set looks like, a subset of the hypercube, and it always contains the structure. Now, I don't know, how crazy is that? Okay, any questions about this?
There's a question, just one moment.
Yeah.
Hello. Yeah.
I can hear you. Yeah.
So this robust Talagrand property, is it known about the undirected case before the directed case was explored?
Good question. No, it was not known.
Okay.
So actually, when Kottminzer-Safra, in the interest of monotonicity testing, introduced this robustness, and of course, as I said, the directed version implies the undirected version, and the robust directed version implies the robust undirected version. What they do is also they give a direct proof of the robust undirected version, which is like maybe about 2 pages long. So once you know what to prove, setting it up is not that difficult. It's like a proof by induction. It's an excellent question. Yeah. Any other questions?
That's it for now.
Okay, all right. So Akash, on time. So I have what, about 5 minutes left or 10 minutes?
10 minutes.
10 minutes left. Okay, so I guess we'll reconvene after the break anyway. But let me give you a very quick flavor about what any of this has to do with monotonicity testing. And it's unlikely I'll finish in 10 minutes. So, I'll maybe give you a high level description and then we can proceed from there. So what we really wanted to do at some point was to analyze this path tester, right? Which is like, if I do this random walk of a given length, how do I escape a set that is far from monotone? So, okay, so I'm going to introduce a few definitions here. It's a bad idea towards the end of the talk, but anyway, I think, I don't know. Most people are awake, seem to be following. Questions are good. So I think the situation is fine. So I'm going to call a walk L persistent. It's an upward random walk. If an L length random walk stays within the f of x region. Okay, so x is L persistent if when you take a random walk of length L, if you start in green, you roughly stay in green. That's what a green persistent. A blue persistent one is if you take a random walk, then you stay within the blue region. Again, with high probability, right? So maybe there are a few walks that escape. But a persistent walk is a persistence vertex is one, where if you did a random walk from their vertex, again, directed random walk, you stay in the same region. Now, let's do a very simplistic analysis. What is the probability that a single step changes value? It's roughly the influence divided by d. Like if you picked a random point, its degree of leaving a set or entering the set is the influence divided by d, which is the degree. Just, what is the probability just by union bound? What is the probability that if you took L steps, one of them changed value? That would be L times influence by d. So by sort of a Markov argument, the fraction of vertices that are not persistent is basically O of L times influence by d. So again, like, if you can't follow the Markov, don't worry about it. Essentially what it says is, look, if the influence is really small and the walk of the length is small, this whole quantity is really tiny. And this is the probability that any one of this L steps changes value. Which means what? It means that all the steps did not change value. And so you can basically turn it around into a fraction of, you apply Markov inequality, and you get that the fraction of non-L persistent vertices is L times influence by D. So and you can also show using some Fourier analysis that if the influence was much, much larger than square root T, then the directed influence is also greater than square root T. So the edge tester already works. So what this says is, because the influence is O of root T, the fraction of non-L persistent vertices is really L divided by root T, where L is the length that you're walking. So if you walk very short, the fraction of non-persistent vertices is really small. Which really means that most of the vertices, if you do a walk of length, less than root T, the value never changes. You're never leaving the set. And so just a quick rundown of the analysis. So the robust Talleyrand theorem says that the boundary looks like this regular bipartite graph. 2 to the d divided by r, all degrees are r squared. We said the fraction of the non-persistent vertices is L divided by root T. Now, I'm going to sort of pick these parameters in a way that's just going to make this work. If I set the length to be square root T divided by r, where the r is the same r over here, then the fraction of non-persistent vertices is 1 over r, which is much smaller than the number of vertices. So the non-L persistent for this length, of course, I don't know what r is, but I can basically search for it, is some small fraction of the boundary. So most of the boundary is persistent. So I can basically remove this small non-persistent part out. Because this is a regular graph, if I remove a small fraction of vertices, I only remove a small fraction of edges. And this is the key. So think of it as what you have is a non-persistent vertex is badly behaved in some way, because it's when you take a random walk from there, it could do anything. It could change value. But the fraction of the non-persistent is a small fraction of the boundary. Hence, I can remove them from the boundary. And because the boundary is regular, I don't damage the boundary that much. So like this reddish portion, the bad portion of the boundary is actually quite small. And so what this means is that the number of vertices in this nice boundary is 2 to the d divided by r. All the degrees are r squared, and they're all persistent, which means if you took an L length walk from there, the value does not change. Okay, so now the analysis in 2 slides, not 1. So we're doing this walk, which is of length, let's say like, root t by r, which is, just to remind you, we set the length to root t by r so that this fraction of non-persistent becomes less than 1 over r so that we can remove it from the boundary. So the fraction of L persistent is little o of root t by r. This is like a regular graph now. All the degrees are r squared. So if I picked a random vertex on the green side, which is the ones, with probability 1 over r, I would start in this part because that's the size of the vertex boundary, right? With probability 1 over r, I start here. With probability r square over L, I flip a bit because I'm doing a walk of length L, and there are r square bits that I can flip, that because the degree is r squared. Essentially, if you do the math with probability roughly r square over L, you'll flip that relevant bit, which plugging that value of L gives you r over root t. And so with that probability, you're going to flip that bit, but then the rest of the walk is going to be persistent. So with the probability r square over L, you actually will flip the bit that takes you outside, and then it's all persistent, so you're fine. And so when both of these events happen, the function value y is going to be 0, at x is 1. And so the total probability is like 1 over r to basically start in that region, in the boundary. And then r square over r over d is to basically flip that bit, and you get a 1 over root d bound. This is like a very simple cartoon picture of how the analysis works. And note that it's kind of magical that the r square over here kind of gives you, cancels out with that and cancels out with the other r, and they all cancel each other out independent of r, and they give you a 1 over root d. And indeed, this cartoon picture that I showed can be formalized with some effort. And that is really how the directed Talleyrand leads to a 1 over root d tester analysis. So this is actually a pretty good point for me to end, even though there may be a few minutes left, because this sort of covers what I wanted to talk about the hypercube. Akash, so I'm roughly at the end of time, right, for this session?
Yes.
Okay, perfect. So let me end over here. I'll take any questions that you have, and then the second part, we'll do something else.
So let's thank Seshadhri. So Seshadhri, I have a question.
Yeah.
So, you mentioned that, this bipartite graph is regular, and you argued that the fraction of non-persistent vertices is very small, and so we can dispose of it. So, but where exactly did this regularity condition become relevant? You just said that the fraction of edges remaining inside the part which is still there is fairly large, but we could have weakened this condition, no? We could have weakened this demand that this graph better be regular.
Yes, you can have essentially what you want is that by removing a small fraction, you don't remove most of the edges. And you're right that you don't need regularity. Something weaker is good enough. And indeed, the Kortmans-Safra paper gives that condition. The benefit of that weaker condition is you only lose a log d and not a d to the little o of 1. The regularity is actually in our analysis later on for the hypergrids, we need the regularity because the analysis is more tricky. But you're absolutely right on that. Just for this, you can have something somewhat weaker than regularity. But on the other hand, the thing is, the truth is you get the regularity by Talleyrand.
I see.
Or some sort of approximate regularity.
Right.
Think of it more like, rather than the fact that I need it, the fact that it is actually true.
Yeah.
Yeah.
Other questions? There is one.
Why do we care about the persistence of the rest of the walk to y on the next slide?
This part.
Yeah. So once we've crossed the boundary, we've already found a proof of right?
Good question. No. So the thing is, remember that you're doing a long walk and you only query the endpoints. You don't query what's in between. Right? Because the tester basically says start at x, do a walk of length root d, and then query y. So maybe you went in between, you crossed the boundary, but then you went back in.
Right. We are allowed to travel more, but we are not allowed to query only a few points.
Only the endpoints, exactly.
Okay. Right.
Yeah.
Thanks.
Excellent question. Excellent question.
Other questions? Okay, so let's thank Seshadhri again.